Welcome everyone. This is Kamada Alex, and I will be introducing to you our knowledge guided large visual model for autism screening in the source constraint settings. So, I'm a member in a team of 3, and today I'll be talking about a model which we have developed to screen for autism, and I'll be explaining to you why we had to develop it. So, I'll be talking about our problem statement, a lot of things. So I'll be talking about technology guidance, supervised classification. I'll be talking about visual data, video analysis. So these are some of the works of people who have tried to do something. So after reviewing some of these works, most of these works had limitations. Either they were architectural limitations or context limitations. So that's why we had to develop a model. And our main application problem is that autism screening, like screening for autism, requires experts, and our clinics lack access those trained experts, those trained specialists, and the methods we use are manual, inconsistent, and often inaccessible. So there is need for an automated AI system which is going to assist these clinicians in early autism detection. So our computational problem is that screening for autism through video analysis, that is analyzing videos, involves complex multimodal data because the video can have a lot of data which can be used in very many models like skeletons, optical flow, and the existing systems we have are computationally heavy. They just capture only one model, and most of the times they lack explainability. So the challenge we have is to design a model which is lightweight, explainable, and multimodal. And the model must be perform accurately. So as we move on, our research objectives first, we had 4 objectives, and the first one was to integrate clinical knowledge into these models we are building, and then we analyze the performance of the models as they keep learning. Then we have to develop a system which could screen for autism through just videos. Then our first objective was to model an affordable and scalable system in low resource constraint settings. So the questions, research questions are we ask ourselves what behaviors distinguish children who have autism from those who don't have, and what features can be captured by our models, and what models can capture those features, and what strategies can we use, what computation strategy can we use to ensure that our system remains interpretable, lightweight, and deployable. So our contributions, we have developed a knowledge guidance framework because the data sets existed, models existed, but our knowledge guided framework was from our research, and we contributed it to the general research field. So, and we had other contributions like developing the models, developing a feature fusion model, a behavioral corpus. So, when I move the methodology of our system, this is how our system works. The user uploads the video, then the video is pre-processed. Then after being pre-processed, it is fed into our inference engine. This is where we find our models, the 3 models, the TSN, SGCN. I'll be talking about them, and the STGCN. Then after they are fused, after we do the knowledge guidance, and we output a report. So this model, this whole system is deployed as a fast API app. So talking about the models, first of all, I'll begin by talking about the STGCN model. So the STGCN model it refers to the spatial-temporal graph convolutional network. Spatial-temporal, as you can see, spatial meaning space, then temporal meaning time. So it does spatial convolution first. After doing spatial convolution, where it captures the spatial relationship between body joints, remember it maps body joints, then identifies how is this joint related to the other joint, how is this joint related to the other joint. Then after it does the temporal convolution, like to detect if someone is how you're moving your joint. Well, it can say this joint at this point was here, then now it has moved downwards, so that is the temporal part of it. Then after doing spatial convolution and temporal convolution, that is what we call a spatial temporal block. So we start like 3 of these blocks. Then after that, it goes into our regression head. That's where we can now predict the ADOS score or the autism score. When I talk about the SGCN model, basically it is the same as the SGCN model, only that it doesn't capture the temporal part of it. So this one also still maps the human body as an adjacency matrix of joints. Then after mapping the human body, it will still understand the relationship between those joints. To understanding the relationships, then it will develop the features. The features are the relationship between those joints, and then they will be fed into our regression head. Then that's where we can predict the ADOS score. So the TSN model, it is different for it to capture optical flow. So basically, it divides the video into several segments, and then for every segment, it extracts out the features, the motion views. So after extracting out those features, it aggregates those features across the different segments. After aggregating them, then they are fed into our regression head, where we predict the ADOS score or the autism score. So this data set we used, it was an MMSD data set, that is multimodal autism screening data set. So this was the data set which captured features from 32 children, and those features were divided in 2 classes. We had the classes like arm swing, as you can see here, the classes. So first of all, we did an EDA on those data sets to explore them and eliminate anything we don't want. So these are some of the results on that data set. After we train the model to recognize the features, and this is the precision recall and F1 score. So after training our models, this is how the models learned. This was the STGCN model, the TSN, and the SGCN. So we didn't capture things like F1 score as what, because this was not classification. We decided to do regression on a scale of 1 to 10. So we captured the mean absolute error, the mean square error, the root mean square error, the mean absolute error. So we have the TSN, SGCN, and the STGCN. So these are some of the graphs of how the model is performed. And from the insights we can learn that these models were performing well. They were learning, and this is how comparison of the 3 models. Then this is how the fusion model scored against the best model. So model selection, which model do we select? First of all, we had the 3 models, but each model was doing a different task. So we deployed the model which integrates all those 3, and that was our fusion model. And this was our deployment pipeline. Now we deployed the model. So It was a fast API app and it has a web interface, so it was deployed on Railway. So is our model is working. Machine learning operations, we have GitHub here, we have logging here. So our demonstration of the model, I will demonstrate for you in a video. Then the limitations we faced, first of all, the models were complex, they required high computational power, they were heavy, especially the STGCN and the STGCN models. Then restricted model evaluation, like testing was done on just this controlled data set. We had to do testing on real world, on a varieties of people. So that is in our future work, like conducting testing across, not just being limited to this data set, across populations. In conclusion, our model worked well. The SGCN, STGCN, and TSN were proved that they were effective, and our knowledge guidance system is working. So in the future, we hope to expand the data set. We hope to get clinical validation. We hope to involve other models. We capture other things like audio cues. So yeah, some references from the work I've been talking about. So I will end by acknowledging our lecturer, Dr. Garwang Marvin, for his guidance and support in all this work, and other contributors like providers of dataset, the Department of Computer Science, the Kaggle communities. Thank you.